The way we control light has changed from a simple switch. As we advance into more complex interfaces, the ways people interact with the system changes as well. Adaptive lighting is a new energy-saving method that uses sensor data to gather information from ambient light and controlled light in order to find an optimal configuration that would minimize energy output. Using solid-state fixtures, otherwise known as LED lighting, our previous research has made adaptive lighting even more energy efficient. However, in our usability review, we found that users change their lighting levels less than once a month, and the lighting levels they choose are oftentimes below optimal settings. This can lead to low task performance and eye health issues. In order to address this issue, we researched human factors affecting user participation in lighting and have developed Lumos, a vision-based system that uses the natural relationships between objects and humans to promote healthy lighting levels. In the design of the system, we found that the human eye perceives brightness much more differently than a sensor. We decided to map our system to the L-star channel of the LAB color space, which can be derived from RGB images. The L-star channel models the human perception of brightness. We decided to incorporate a gesture recognizer and a colored object tracker to create a human object interface. Our gesture recognizer used orientation histograms to classify open hand, pointing hand, and closed fist. However, we found that although gestures are one of the most natural means of communications, gestures are unnatural with digital systems. We incorporated a color tracking method that was able to find heavily saturated objects, such as post-its under low lighting. In combination with gestures, we created a human object interface which based communications with the digital system on the behavioral patterns users have with objects. We begin by adding functionality to trackable post-its, such as a switch that would wait for a pointing gesture. And we embed these functional post-its onto objects. The green post-it bookmark triggers the lighting system to adjust to recommended reading light levels. Technical drawing is one activity which requires a significant amount of light. The eraser here acts as a technical drawing light preset, where if the system detects the color cue on the eraser is occluded for a certain period of time, it adjusts the lights to optimal conditions. The correct computer lighting level is especially important for task performance. Embedding color cues on a mouse or keyboard takes advantage of natural human behavior. By embedding a color cue on an object that you always take with you, such as a cell phone, keys, or a watch, a system can know when to turn on and off lights, maximizing energy savings. Furthermore, if a user looks back and sees that their lights are still on, then they know that they've left their object, be it a cell phone, keys, or their watch. To allow greater user interaction, we included a dimmer, which waits for a pointing gesture to initiate, and a closed hand to set. Lastly, a region selector allows for a specific area to be optimally illuminated. We use the simplex linear programming algorithm to find the optimal configuration so that lighting levels are always constant, even when ambient light, such as a lamp, enters the scene. Thus, a new type of relationship emerges with the user and the system. And by incorporating human factors into adaptive lighting, we can reach both energy savings and optimal lighting conditions.